Okay, we did. I explained the concepts behind logistical growth in video one. In video two, we did two examples. We're going to try to do two more here in this last video on logistical growth. And you'll start to see once we do a third and a fourth example, certain commonalities in terms of, what's asked, how the information is actually expressed, and all sorts of fun stuff like that. Okay. Here is our third example. And again, we're actually given it as the function, not the differential equation. So the spread of a disease through a community can be modeled with a logistical equation, and it's given, where y is the number of people infected after t days. Now, we need to be careful because our formula is p of t, m 1 plus a e to the negative kt. There has to be a 1 right here. There's not a 1 right there. We have y is equal to 5,400 over 3 plus 99 e to the negative 1.5t. Now, that's nice because all of those numbers are divisible by 3. So I can actually get to here, okay? This is actually what we want to deal with, not this, okay? And from here, we can surmise that m is equal to 1,800, k is equal to negative 3/20, or negative 0.15. Your a is 33, and you can do all sorts of calculations. But here's the thing, okay? This is obviously, we're capable of getting it. Let's go see what they actually ask for. Now, this obviously, they're using a different book, okay? K is obviously the same, but C is what they're using for A, and D is what they're using for M, okay? And we found all of that material. We found the carrying capacity, which is what they called D. We found K, and basically what they called C, our book, the Stewart book, called A. So this is all the information that was actually asked for in part A of that question. Now, how many people are infected when the disease is spreading the fastest? Are you noticing a trend here? Because they are always asking a question about that point of inflection. Okay, so if we happen to have this right here, 1,800 is the carrying capacity. What is the population when at the point of inflection? Well, it's halfway up. It's 900. You're done. Okay, that's it. So that question was actually extremely, extremely easy. Okay. Let's go ahead and let's look at, actually we may be able to squeeze in more than just one more. Let's go ahead and try to squeeze in this one, and then we'll actually get to an AP question that was asked back in 2004, okay? A population is modeled by a function p that satisfies the logistic differential equation, and it's given. Find the carrying capacity C. Okay, so I was wrong. C wasn't A, C was M, but whatever, okay? So, carrying capacity C. Well, what's the carrying capacity? Well, we do have it in the form that we need it in. The form that we need it in is dP dt is equal to Kp 1 minus P over M. So in terms of our variables, our K is equal to 1/8. Our M is equal to 12. Okay? Now, let's go ahead and let's move on from here. So the carrying capacity is our M. We've answered that. Find the constant K. We've answered that. What is the population at the time when the population is growing the fastest? I've seen that question before. It's half the carrying capacity, so it's when P is equal to 6. So here is A, here is B, C is P is equal to 6. Find the logistic model P of T given an initial condition of P of 3 is equal to 3. Okay, now remember, my A value is M minus initial population over initial population. I was just given initial population. P naught is 3. And therefore, in this particular case, it's 12 minus 3 over 3, or 3. Which means that I'm basically just going to take this information and I'm going to plug it into P of T is equal to M over 1 plus A e to the negative kt. That means my P of T for this particular problem is 12, that's my M value, 1 plus 3, that's my A value. A, what's my K value? It's 1/8, so it's either 0.125 or negative 1/8 t. That is the function. Okay, well that one was easy enough. The one that's asked on the AP exam is a little bit more difficult, so let's go ahead and take a look at that one. It's got a few more pieces to it. Now, this one actually gives it to us, and it says scoring guidelines because that's just the way I printed it off. The reason I have it folded up is the fact that the actual way that they score it and how they apportion the 9 points for each free response question is on the back. A population is modeled by a function p that satisfies. Well, thankfully, they've given us where it's 1 right here. So I can just read k and everything else right off of it. Now it's asking if the initial position, if the initial population, if P naught is 3, what is the limit as time goes to infinity of P of T? Okay, now what is that really asking? What it's really asking is this, okay? It's asking for the carrying capacity. Now, is the carrying capacity going to be different if it's one of these? No, it's really not. The carrying capacity is always the same. Think about a population of, I don't know, gerbils. Let's say field mice, okay? Population of field mice in a particular field, that the carrying capacity for that field is 200. If there's 50, the population will eventually get to 200. If the population is 300, the population will eventually decrease to the carrying capacity as well. So it doesn't matter from what side you're dealing with, okay? It will either come down from the top or it will come up from the bottom to meet the carrying capacity. Because notice that 20 right here is larger than 12. Right here, it is above carrying capacity. But that doesn't matter. Carrying capacity refers to what the population will either rise to or come down to, decrease to, over time as t goes to infinity. So the answer for both parts of part A are the same. It's 12. Okay, that's just a creative way for them to ask you about carrying capacity. Now, does the part B look familiar? If P naught is equal to 3, for what value of P is the population growing the fastest? Does it really matter what the initial condition is in order to find that point? No, because all P, here's the thing. It doesn't matter. The initial population, the P naught, doesn't really matter. The only thing that the P naught gauges is whether the y-axis is here or whether the y-axis is here. Either way, it really doesn't matter, okay, for the inflection point. Now, granted, if it's past the inflection point, then it's increasing the fastest at its initial condition. But so long as the initial condition is prior to that point of inflection, it's the point of inflection, okay? And obviously 3 is below 6. 6, of course, is half of that carrying capacity. So if 3 is below 6, then your answer to part B is the fact that population is growing fastest at P is equal to 6. And if you wanted to, you could actually, go in and find when that is. Of course, they haven't asked you to do that. What they do in part C is they throw you a curveball. They, in part C, introduce a new differential equation. A different population is modeled by a function y that satisfies the separable differential equation. Now, notice the difference. This is not logistical growth. Because here you have P here and P here. Both of these are the output variable. That is consistent with our formula. Here, this is output. This is input right here. So as a separable differential equation, this winds up being 1/5 y, 1 minus t over 12. The y goes down here, and I get dy over y, and this becomes 1/5 minus 1/60th t dt after I distribute that 1/5 and multiply both sides by dt. Well, let's go ahead and let's actually figure that out. This becomes natural log of y is equal to 1/5 t. Okay. Now, remember that this is going to wind up being, if we actually wind up doing this, this is going to wind up being t squared over 2. So it's 1 over 120 t squared plus c. Now, when I exponentialize both sides, I'm going to go ahead and do that leading coefficient, which is the e to the c, right? And so we have y is equal to a e to the t over 5 minus t squared over 120. Now, it says find y of t if y naught is equal to 3. Well, that's really, really easy. All you have to do is just plug in the numbers and solve for a. Okay, so we know that the output is going to be 3, and we know that the input is going to be 0. So a is equal to 3. And so y is equal to 3 e to the t over 5 minus t squared over 120. That right there is the answer to part C. Now here comes the rough part. For the function y found in part C, what is the limit as t goes to infinity? Well, notice that as t goes to infinity, this term of the exponent is going to increase much faster. And you can actually do it like this. Okay? This denominator is going to increase much faster than the numerator. So the limit as t goes to infinity of y of t is going to be 0. That denominator, since it's e raised to a quadratic instead of e raised to a linear, that denominator is going to increase so much faster than the denominator that it's eventually going to drive that value towards 0. Okay, and that winds up being our value. So in total, we've gone through 5 examples of this. I think I've communicated how important it is to understand that point of inflection, which is halfway up to the carrying capacity. Basically, it's one of those ones where as much as I love the concept, it's a waste of time to actually integrate it by hand. You need to memorize the formulas, no matter what variable they're associated with. If m is called m or if m is called c, it really doesn't matter. It's still the carrying capacity, okay? So go ahead and memorize how that information transfers back and forth between the differential equation and the population function. And I think you'll be in good stead. Basically, these wind up being very, very predictable. All 5 of the ones that we walk through are very, very standard. The only thing on the AP one is they gave you a non-logistical growth one on C and D and asked basically, in A and B, do you know how to deal with logistical growth? In C and D, do you know how to deal with differential equations in general, even when they kind of look like logistical growth, even though they're not. That basically wraps up our talks about logistical growth. I hope that's been helpful. Email me with any questions that you might have, and good luck on the test. Bye.